Okay, we're going to look at something called vectors, and a vector is different from what's called a scalar quantity, and I'm going to go through that more in class of what the difference between a vector and a scalar is. But for now, I'm just going to show you a brief introduction to how to add and subtract vectors. Well, imagine I had certain vectors here, and I'm going to draw it something like this and say here's one vector, vector A. There's another one. Call this vector B, and another one here, we'll call this one a vector C. So these three vectors here, A, B, and C, they go in different directions, and direction is important here. They start somewhere, end somewhere, start somewhere, end somewhere, etc. The question is how to add and subtract these. Well, if I have a vector here, and I do, let's say A plus B plus C, and I want to find out what these three vectors add up to. What you end up getting is, well, if I draw this, you're going to get, there's vector A. Now, when you add B here, you always start at the end. In other words, this is called the tail and the tip. Okay, and so here's the tip of it. Right at the end of this is where I would start B. So it's like I picked this up and brought it over here. So imagine I just took it in the exact same direction, and there's B, and then I can also add C on top of that. So here's a rough sketch of this. From where I started to where I end, this is where the direction of the resultant vector would be, what I'm going to call R. So in other words, these three vectors, okay, when I add them up, they end up giving me this resultant R. And of course, there'd be some angles we could calculate later. But right now, that would be my vector resultant R. Okay. I could also do something similar where I would do maybe A plus B minus C. Now, what does a minus do? Well, I do the exact same thing again. There's A, here's B. Now the difference here is that instead of going down, this vector here, you see C is going down, what I'm going to do is actually flip it. A negative C just means I'm reversing direction. Same size, but I'm reversing direction. So maybe there would be C. Maybe in a different color here. Maybe I'll use green to indicate now that the resultant would be starting at there, ending there. So I'm going to go up. And there would be my resultant. It doesn't matter that it crosses paths here. This is where it started, this is where it ended, and that would be my resultant vector, R, that dotted line there. You can also multiply vectors by what's called a scalar. And so, just to show you how that looks, if I do something simple like, let's say 3 times A minus 2 times C. What would that look like? Well, 3 times A is going to look something like this. Now I'm going to actually take a separate piece of paper here. So what it's going to look like is like this. 3A would be, well, there's 1A. There's another A. There's another A. And then minus 2C. Well, if we remember, if we recall down here, that C is pointing down. So minus would be 1C, 2C. And it looks something like that. And then, of course, my resultant would be starting at the tail end of this and going to the tip. And that whole thing in a straight line, if I had a ruler, would be my resultant R. So you can get 3A minus 2C. You just add, it's like doing A plus A minus C minus C. That's what you're doing right here. So you can add them up in that direction. Similarly, I could do examples like A minus A. Of course, that's going to give me 0. Because if I showed you, you're going to get A. Well, minus A, if I do it in a different color here, would go start at the tip all the way back down, and I'm going to be right back where I started, and that's why I end up getting 0. So there's a brief introduction to basic vectors. Another thing you can do with vectors is find angles and break them up into components. I'm going to show you that here. So if I have a vector, same thing, I'll call it vector A. Okay, here's vector A. What I can do is I can break this up into what's called components. Because this is at an angle, now normally we like to deal with x and y axes, in other words horizontal and vertical. It's nice and easy. But when they're at an angle, it becomes a little bit more complicated. So what I do is I just arbitrarily choose an axis. So I'm going to say, well, let's make the horizontal here my x, my reference point. I'm going to call this theta. So there's theta. What I'm going to have here is that I can break them up into this vector into horizontal, in other words in the x direction, and in the y. And notice I'm going to call this AY and this one AX. Okay, AY and AX. Now notice here that these vectors add just like they do before. Here's one vector, here's another vector. This would actually be my resultant now. The big A would be my resultant. So AX plus AY, AX plus AY would actually give me A. And you'll notice, well, how do I calculate that? Well, I'm going to have to use Pythagorean Theorem. In other words, to get the magnitude of A, okay, to get, and this symbol here means the magnitude of A, I'm going to have to say that's equal to AX squared plus AY squared, and then square root that. Okay, so you end up getting something like that for the Pythagorean Theorem. But what does this angle have to do with it, and how do I calculate AY and AX? Well, if you notice here, AY is going to be equal to, well, I notice that this is going to be the sine of theta is equal to AY over A. In other words, I'm just going to write that out here. The sine of theta is equal to AY over A, which means AY is equal to A sine of theta. And similarly, AX will be equal to A cosine of theta. These are very useful when solving into components. Okay, these are very, very useful. The reason being is because I can get two vectors that are awkward to add up. Something like this. So I'm just going to cut this off here and do another example. Well, you know, suppose I had the same thing. I had, you know, vector A, and is at some angle. And then there's a vector B here. And vector B is completely horizontal. Okay, so there's vector B. It's completely horizontal. We're going to divide this one up into components. Okay, let's write down the word here. It's called components. Okay, so components here. Well, I'm going to get here an AX and an AY. Now, when you add vectors, you can't add X and Y directly, only with using the Pythagorean Theorem, but you can add all the X's and all the Y's separately, and then find the resultant later. And I'll show you what I mean by that. So, if we're going to look for the resultant, which would, you know, end up being, well, the vector started here, ended here. So this actually would be my resultant R. I'm going to try to figure out how to calculate the length of that. What I would do is to say, well, AX, this is equal to A cosine theta, AY is equal to A sine of theta. So I know those in advance. I know that B is only in the X direction, so I'm just going to call it BX. There's no Y direction of B. It's completely horizontal. So when I add up, let's say in the X direction, okay, you're going to get here that Rx is actually equal to, the resultant of X is going to be equal to AX plus BX. And in the Y, RY, pardon me, that's RY is equal to AY, and there is no BY because it's all 0, so it's just equal to AY. So if I add these up again, I'm going to get AX, so here's AX, plus BX. Now I add it to AY. So what I'm doing here is I'm saying here's AY, here's AX, and here's BX. When I add up these three, and I notice I moved them around, instead of doing at an angle here, I've taken this component with this X first, and then added the Y after. I'll get a resultant that looks like this, and you'll notice that it's exactly the same resultant. These are identical, but this looks a lot prettier. It's a lot easier to add up. Now, if I needed to do some math, I could say, well, AX plus BX, find this number, and then use Pythagoras, just like I did before, to calculate what the size of this is. And maybe I have to know an angle as well.